Hello everyone, today I'm going to talk about my recent research on tungsten speciation in hydrothermal all-forming fluids. We're interested in tungsten in minerals and fluids because most of the tungsten are mined from hydrothermal tungsten minerals. They exist as tungsten 4 plus or tungsten 6 plus. That's the two major oxidation states of tungsten in the mineral. And most of them are from sodium chloride dominated brines at the temperature of 200 to 400 degrees. We need to understand the tungsten complexation in aqueous fluids over the wide range of temperature, pressure, and chemical composition to help us to understand all formation. However, there are not much molecular level studies on the mechanism of tungsten complexation under hydrothermal conditions, especially the role of sodium chloride, the sulfur, and the fluoride in aqueous tungsten species. So the aim of this research is to understand the chemical control of tungsten solubility as a function of pH and sodium chloride, fluoride, sulfur concentration. The technique we use here is called the molecular dynamics simulation. So this method is based on fundamental physics and chemistry. Basically, we put the box and we put all the particles we're interested in this box, and all the particles will move according to density functional theory to define their interactions. So from the simulation, we can get an independent check of experimental studies, and also we can predict metal speciation beyond experimental conditions, and also calculate the thermodynamic properties such as log Ks to use for further geochemical model. These simulations are quite consuming in terms of CPU hours, so we need to use a supercomputer. These two supercomputers are the machine I use in Australia. So first of all, let's look at the tungsten chloride complexation. So we start the 3 different boxes with different chloride concentration and using 2 different starting composition. One is the tungstic acid and another one is tungsten with 4 chloride to test the stability of tungsten chloride complex. So here is an example of the stability of tungsten chloride species we test at MD. So as you can see from this video, we start with tungsten with 4 chloride and let it go and see how it's going. So this picture here shows the dynamic process of tungsten chloride and tungsten oxygen distance as a function of the simulation time. We can see at the beginning of the simulation, we have 4 chloride in surround tungsten, and then there's 1 chloride left and only 3 chloride surround by tungsten. At the same time, 2 oxygen is here, and with the simulation going on, there are another oxygen. So this oxygen has a water attached to tungsten, and then this water left again, and still 3 chloride and 2 oxygen with the tungsten. Finally, all the chloride just left regularly and only leave tungsten with 4 oxygen as the final species. So this final species looks like that. This simulation showed us tungsten chloride species is not very stable. And we also use the synchrotron to test that. We prepared the different solution with different chloride, sodium, and tungsten concentration, and we look at the spectrum. So we only can see the tungsten oxygen bond, so there's no tungsten chloride bond. That shows us the predominant species is tungsten acid with different proton. It depends on different pH. So let's look at the tungsten fluorine. That's a different story. So we start the simulation box with 3 different initial configuration with fluorine from 0 to 2. And then we look at the simulation result. We saw the major species from 0 to 2 fluoride, and also there are some minor species. For example, this one has 2 more oxygen, and this one there's a proton attached to this oxygen, shows some pH dependence. We're interested in these 2 species here, and we calculate the free energy using a technique called the thermodynamic integration. So from this calculation, we can get the homohost free energy, and then we can convert that to log K of these reactions. We put this log K into the thermodynamic database, and then we can plot this activity diagram as a function of pH and fluoride concentration. So from this diagram, we can see the tungsten fluoride species like this one or this one are predominant in high fluoride concentration under low pH. So that shows tungsten fluoride is really important species in hydrothermal tungsten transport. We also look at the tungsten sulfur species. So we test this box at 3 different temperature and start with 0 sulfur to 4 sulfur. We run this simulation, and we found the tungsten sulfur species is a really nice tetrahedral structure. So the sulfur just replaces the oxygen, but the distance between tungsten sulfur are quite longer than tungsten oxygen, so it's quite identical. So we can see the difference from a synchrotron, which we did. We look at the tungsten sulfur solution at the synchrotron. We prepare the solution with different sulfur concentration, and we measure the spectrum at the different temperature. So from this diagram, we can see there are 2 peaks. One shows the tungsten oxygen, and one shows the tungsten sulfur. So tungsten oxygen peak increase with increased temperature, and the sulfur peak decrease with increased temperature. And we can also see from the different sulfur concentration, if there are more sulfur in the solution, the tungsten sulfur peak is higher. So this simulation and experiment shows that the tungsten is really, sulfur is really important in tungsten transport. So the cell tungsten species are very important. So that's will give us more information about tungsten and sulfur interaction. So final conclusion and the takeaway message is we did the simulation and experiment of tungsten in chloride, fluoride, and sulfur-rich fluids, and we found there are no tungsten chloride complexation, but fluoride and sulfur are quite important in tungsten transport. We can use this information and these thermodynamic properties to map the tungsten solubility as a function of temperature, pressure, pH, and the concentration of chloride, fluoride, and sulfur ion. So that's all for today, and thank you for listening. Please come to the Q&A session if you have more questions. Thank you. Bye.